if you are engineering inference pipelines for large language models or building massive scale vector databases, you are intimately familiar with the ultimate memory bottleneck.
Oh, absolutely. The key value cache.
Right, the KV cache. As context windows scale into the millions of tokens, memory bandwidth just severely chokes the hardware. You are forced into this really brutal trade-off.
Yeah, you basically have two bad options.
Exactly. You can either utilize offline data-dependent methods like product quantization using k-means, which gives you great compression, but the pre-processing times are entirely intractable for online inference. You just can't do it on the fly.
No, it's way too slow.
Right. Or you fall back on naive scalar quantization, which is super fast, totally accelerator friendly, but, and here's the catch, it subjects your model to suboptimal theoretical distortion bounds, so you're directly degrading the output quality.
I mean, that tension between computational latency and theoretical distortion limits has effectively paralyzed the vector quantization literature for online applications because you simply cannot afford the latency of data-dependent clustering while generating tokens. And you also can't accept the retrieval degradation that comes with standard scalar methods.
Which brings us to the actual mission of this deep dive. Today, we are analyzing a really elegant solution to this exact bottleneck. We're looking at a newly published paper titled TurboQuant, Online Vector Quantization with Near-optimal Distortion Rate.
Yeah, this is from researchers at Google and NYU.
And it's fascinating. They've developed a data-oblivious, fully accelerator-friendly algorithm. It essentially bridges Claude Shannon's 1948 source coding theory with the very stark architectural constraints of modern GPUs.
It really does. And to achieve this optimal quantization without even looking at the data, they break the problem down into two discrete phases.
Right. First, tackling mean-squared error distortion, and then patching a really crucial statistical bias regarding inner products. So let's start with that first part, the MSE optimization.
Yeah, the TurboQuant MSE phase. The initial mechanism here, the engine driving the MSE minimization, relies on forcing completely arbitrary, even adversarial data into a highly predictable statistical distribution.
Okay, so imagine you were handed a worst-case d-dimensional input vector, let's call it x, and it's sitting somewhere on a unit hypersphere.
Right, and instead of trying to adapt a codebook to this unknown, potentially awful vector, TurboQuant just multiplies x by a random rotation matrix. They denote it as pi.
And this matrix isn't just made up randomly, right?
No, it is specifically generated via the QR decomposition of a random matrix that's populated with independent, identically distributed normal entries.
So geometrically, if you're visualizing this, you are taking an arbitrarily pathological, highly localized cluster of input points on that high-dimensional hypersphere and applying a completely uniform randomized rotation.
Exactly. You scramble the coordinates across the entire surface of the sphere.
You're entirely negating any worst-case adversarial input. The data distribution doesn't matter anymore.
It doesn't matter at all. And the mathematical consequence of this operation, which they formalize in lemma 1 of the paper, is really where the algorithm finds its footing.
Right. Because of that uniform rotation, every single coordinate of the resulting vector predictably follows a scaled beta distribution.
Yes. And by invoking the central limit theorem and the phenomenon of measure concentration in high dimensions, we know that as your dimension d grows large, this beta distribution tightly converges to a Gaussian.
Specifically, a normal distribution with a mean of 0 and a variance of 1 over d.
Exactly. But, the convergence to the Gaussian is critical, but the true analytical power here comes from the joint distribution of these coordinates.
Oh, because of the high dimensions.
Right. In high-dimensional spaces, the concentration of measure guarantees that distinct coordinates of this rotated vector become nearly uncorrelated.
Right.
But more importantly, they become nearly independent. That near independence is the exact mathematical lever the authors exploit here.
Because if they don't interact, if the coordinates are independent, TurboQuant can completely disregard all those computationally expensive covariance structures that usually ruin traditional vector quantization.
Yeah, empirical data clustering becomes entirely obsolete. If the marginal distributions are perfectly known to be normal, 0 and 1 over d, you don't need to run k-means over a data set to find your centroids.
You just analytically solve a continuous one-dimensional k-means problem for each coordinate individually.
Exactly. You apply the Lloyd-Max algorithm, but instead of iterating over a discrete empirical data set like you normally would, you perform continuous integration over the known probability density function of that scaled beta distribution.
Wow. So to quantize to a target bit width, say b bits, You partition the continuous interval into 2 to the power of b regions.
Right.
And you compute the exact centroids that minimize the continuous MSE integral. And the absolute beauty of this is that the entire process is offline.
Yes, it's completely data oblivious. The optimal centroids for practically useful bit widths, like 1, 2, 3, or 4 bits, they're computed exactly once analytically and then just stored in static lookup tables.
So when you're actually running online inference, the procedure just reduces to a sequence of really simple, highly parallelizable matrix operations.
Exactly. A new vector arrives. You multiply it by a random rotation matrix pi. You map each rotated scalar coordinate to its nearest precomputed 1D centroid, just a simple table lookup.
Right, and you store those resulting indices.
Yeah.
Then to dequantize later, you just retrieve the centroids from the indices and multiply by the transpose of the rotation matrix.
The computational overhead is practically zero. It fully utilizes the matrix multiplication units on modern accelerators, and it literally never touches a data-dependent heuristic.
It is an exceptionally elegant solution. I mean, formulating the quantization entirely through known distributions lets them analytically bound the expected MSE distortion.
It does. But optimizing purely for MSE creates a really subtle but honestly catastrophic problem for the specific workloads you and I actually care about.
Right, and this is where we have to push back a little on the math, because we have rigorously optimized for mean squared error here, which measures Euclidean distance.
Spatial distance, yeah.
But when we look at the core operations in an LLM, specifically scaled dot product attention, or nearest neighbor searches in an embedding database, the metric of interest is the inner product.
Exactly. Dot products.
And there's this pervasive heuristic assumption in the literature, right? That if you optimally preserve the spatial distance between vectors on a hypersphere, you are inherently preserving the angle between them.
Which would mean you're preserving the inner product. Yeah, it's a super common assumption. And this paper explicitly dismantles it.
They completely tear it down.
They do. The authors reveal that MSE-optimized quantizers introduce a highly problematic systemic statistical bias when you're trying to estimate inner products.
And this bias is particularly severe at the ultra-low bit widths, which is exactly what we need for modern KV cache compression.
Right. So let's trace the mechanics of that bias. Why does minimizing Euclidean distance artificially warp the dot product?
Yeah, let's look at the extreme boundary condition. Say you have a 1-bit quantizer, so b equals 1.
Okay, so we know our rotated coordinates approximate a normal distribution. To minimize the MSE for a Gaussian at 1 bit, the optimal continuous Lloyd-Max centroids are located at positive and negative, the square root of 2 over pi times d.
Okay.
Now, evaluate the expected squared magnitude, or the squared L2 norm, of this dequantized vector. You have d dimensions, and you square each to get 2 over pi times d.
Oh, I see. So the d cancels out, leaving you with just 2 over pi.
Exactly.
But wait, the original input vectors lie on the unit hypersphere, which means their true squared magnitude is exactly 1.
Yes.
But the dequantized vector has an expected squared magnitude of 2 over pi, which is what, roughly 0.63?
About 0.63, yeah. So the Lloyd-Max algorithm, by pulling the centroids inward toward to minimize the squared errors on those long Gaussian tails, is literally shrinking the vector.
It's scaling the physical spatial footprint down by almost 40%.
Right. And because the vectors are physically shrunk, their inner product estimations are proportionately deflated.
Wow. And a multiplicative bias of 0.63 would completely destroy the softmax distribution in a transformer attention mechanism.
Oh, entirely. The temperature scaling would be totally thrown off. And if you're in a vector database, the relative ranking of your nearest neighbors would be severely distorted.
I mean, the bias diminishes mathematically as you allocate more bits, obviously. But at the 1 or 2 bit regime, standard MSE quantization is basically unusable for attention.
Which is why the authors introduced their second major architectural innovation. They call it TurboQuant prod.
TurboQuant prod. So this is a 2-stage algorithm, and it's designed explicitly to patch that magnitude shrinkage.
Exactly. It yields mathematically unbiased inner product estimation. And the stage 1 step seems a little counterintuitive at first glance.
Right, because if your total budget is b bits, you actually dedicate b-1 bits to the biased TurboQuant MSE algorithm we just talked about.
Right. You sacrifice 1 bit from your budget to generate a structural approximation of the input vector. And then you subtract this quantized approximation from the original unquantized vector.
And the result of that is your residual vector.
Exactly. The sole purpose of this first stage is just to drastically shrink the L2 norm of the signal you still need to quantize. You are isolating the error.
Then comes stage 2. You take that residual vector and you apply a 1-bit quantized Johnson-Linden-Strauss transform to it.
Right, the QJL transform. It operates by multiplying the residual vector by a dense random matrix with independent normal entries.
And then it just takes the sign function of the resulting coordinates, right? So it compresses the residual down to exactly 1 bit per dimension.
Yeah. And the theoretical weight of this two-stage approach lies entirely in the properties of that QJL estimator.
Because when you use random Gaussian projections and take the sign, the expected value of the inner product maps back to the angle between the original vectors.
Right, via the arc cosine law. It is a mathematically provable, completely unbiased estimator for inner products.
That's brilliant. So by applying an unbiased estimator to the residual error and then just adding it back to your first stage approximation,
the expected value of the total reconstructed inner product perfectly equals the true inner product.
you completely neutralize that 2 over pi s.
Exactly. And, if you were to apply the 1-bit QJL transform directly to the raw input vector without the first stage,
It'd still be unbiased, right?
it would be, but its variance would be unacceptably high. It would be too noisy.
So by utilizing the first stage to heavily reduce the L2 norm of the residual, you tightly constrain the variance of the QJL estimator.
Yes. The two stages operate in perfect symbiosis. The MSE stage minimizes the variance, and the QJL stage corrects the bias.
Yielding an optimal inner product quantizer for your full bid budget.
It's remarkably clever.
It really is. But, with the mechanics isolated like this, we need to examine the formal theoretical bounds. Because engineering a clever heuristic is one thing, but proving its mathematical limits requires anchoring it to foundational information theory.
Right. And the authors evaluate TurboQuant against the Shannon lower bound,
which dictates the absolute theoretical minimum distortion that any lossy compression scheme can achieve for a given bit rate.
Yeah. But the challenge the authors face here is that the Shannon lower bound assumes the input data follows a specific, usually uniform, random distribution.
Right. But TurboQuant is explicitly designed to be robust against adversarial worst-case inputs. So how do they bridge that gap?
They utilize Yau's minimax principle.
Yau's minimax principle, which is a profound tool in theoretical computer science.
It really is. It essentially states that the expected cost of a randomized algorithm on a worst-case input,
which is what TurboQuant is dealing with,
is lower bounded by the expected cost of the best deterministic algorithm operating on a specifically chosen random input distribution.
I see. So they flip the problem. And in this case, the authors choose the uniform distribution over the hypersphere.
Exactly. By applying Yau's principle, they can take the Shannon lower bound, which was derived for the uniform distribution, and use it as a rigorous mathematical floor for TurboQuant's performance on worst-case input.
Okay, so through this framework, they formally prove that for any randomized quantization algorithm operating at bit width b, the absolute lowest achievable MSE distortion, the fundamental limit of information theory, is 1 over 4 to the power of b.
That 1 over 4 to the power of b is the absolute floor. You cannot beat it.
So what's TurboQuant's upper bound?
They derive the specific theoretical upper bound for TurboQuant's distortion, and they mathematically prove it to be the square root of 3 pi all over 2 times 1 over 4 to the power of b.
Okay, and that coefficient, the square root of 3 pi over 2, evaluates to roughly 1.53, right?
Right. So when you factor in the necessary dimensionality constants, the expected mean squared error of TurboQuant is analytically proven to be within a minute constant factor of the Shannon lower bound.
It comes out to approximately 2.7 times the theoretical limit.
Yes.
I mean, for an online data-oblivious algorithm to sit within a factor of 2.7 of the absolute mathematical floor of the universe, that's remarkable.
And it gets better because the bounds tighten even further at lower bit widths. At b equals 1, TurboQuant is mathematically proven to be only a factor of 1.45 away from absolute perfection.
Wow. So it fundamentally solves the bit width dependence issue that really constrained all the prior research.
Exactly. Previous VQ methods suffered from distortion bounds that scaled terribly as the bit width increased. But TurboQuant's distortion decreases exponentially with b. It perfectly matches the optimal theoretical rate defined by Shannon.
Okay, but theoretical perfection in a vacuum must eventually be tested against the chaotic, non-uniform activation spaces of actually deployed neural networks.
Oh, of course. And the authors recognize this. They transition their evaluation to empirical validation on Llama 3.18b instruct.
And the primary target here is KV cache compression. They evaluate it using the needle in a haystack benchmark.
Right. For those who might not have run it recently, the needle-in-a-haystack evaluation requires the model to accurately retrieve a specific factual statement buried deep within a massive context window.
And the authors aggressively constrained the KV cache for this, right? They enforced a 0.25 memory compression ratio.
Yeah, they stripped away 75% of the memory footprint, operating at an effective 4x compression.
And under these severe constraints, TurboQuant achieved an exact match with the full precision uncompressed FP16 baseline.
It sustained perfect retrieval accuracy across context lengths scaling from 4,000 tokens all the way up to 104,000 tokens.
104,000 tokens with 75% of the cache missing. That is a stark contrast to existing methodologies.
It really is. I mean, token dropping algorithms like SnapKV or Pyramid KV, they invariably show degradation and recall at specific depths because they permanently discard information.
You can't retrieve what you've thrown away. And standard scalar quantization methods, like KAVI, they lack the theoretical rigorousness to preserve the inner products perfectly. So you get noticeable performance drops in the attention distributions.
But TurboQuant's ability to preserve the spatial and angular integrity of the vectors translated directly into flawless retrieval.
Achieving that parity did require a highly specific engineering implementation, though, which they detail in their long bench text generation results.
Yeah, they didn't just arbitrarily force the entire KV cache into a rigid 2-bit or 4-bit integer grid.
No, they implemented fractional effective bit widths, specifically 2.5-bit and 3.5-bit quantization.
And the necessity of fractional bits stems from the presence of massive outlier channels in LLM activations.
Right, this is a known quirk of LLMs. A small subset of dimensions often exhibits magnitudes vastly larger than the rest of the distribution.
Exactly. And if you blindly apply your random rotation matrix pi to a vector containing these extreme outliers,
oh, the rotation just distributes that massive magnitude across all the coordinates.
It poisons the entire vector and explodes the quantization error.
So to mitigate the outliers, they isolate them before rotation.
Right. For the 2.5-bit configuration, they separate the 32 outlier channels from the 96 regular channels.
And they allocate 3 bits of quantization budget to the outliers and 2 bits to the regular channels.
Yeah. By running 2 parallel independent instances of TurboQuant on these segregated groups, the aggregate memory footprint averages out to an effective 2.5 bits per dimension.
This hardware-aware segregation is critical. The paper reports that at an effective 3.5 bits, utilizing this exact outlier isolation technique, the text generation quality on Longbench was absolutely neutral compared to the full precision cache.
Neutral. You are reducing the memory footprint of the KV cache by a factor of over 4.5 and simultaneously drastically reducing the memory bandwidth required during inference.
Without sacrificing any generation capability.
It's huge, and the implications extend directly into large-scale retrieval systems as well.
Yeah, let's look at the vector databases. The authors evaluated TurboQuant on a nearest neighbor search task using the DBpedia dataset, populated with OpenAI's 1536-dimensional embeddings.
In the vector database ecosystem, the entrenched baselines have historically been product quantization and more recent iterations like RabbitQ.
Right, and TurboQuant consistently achieved superior recall ratios at topping across various big configurations compared to both of them.
It did. But honestly, the recall metrics are secondary to the indexing latency.
This is the crazy part, because product quantization requires executing iterative k-means clustering over the empirical dataset to construct its codebook.
Yeah, for the 1536-dimensional DBpedia dataset, PQ required approximately 239 seconds to index. RabbitQ required over 2,200 seconds.
And because TurboQuant is entirely data-oblivious, relying solely on the randomized QR rotation and those continuous offline Lloyd-Max integrals, there's absolutely no clustering phase during indexing.
None. The algorithm's time complexity for building the codebook does not scale with the dataset size. TurboQuant's indexing time was reported at 0.0013 seconds.
0.0013 seconds. The algorithm is natively vectorized, mapping perfectly to GPU tensor cores, resulting in indexing speeds that are 5 orders of magnitude faster than empirical clustering methods.
It's a total paradigm shift. Synthesizing the architecture of TurboQuant really reveals a highly deliberate progression of mathematical logic.
Right. They neutralize adversarial distributions through random rotations. They exploit high-dimensional measure concentration to enable continuous offline 1D k-means.
And then they architect the 1-bit QJL residual transform to perfectly patch the inner product bias inherent to MSE optimization.
The result is an online, highly parallelizable vector quantizer that essentially achieves the Shannon lower bounds in practical deployment.
And for you, listening to this, managing deployments of models with context windows rapidly expanding beyond 1 million tokens, theoretically grounded quantization, is transitioning from an optional optimization to a strict structural requirement.
The memory bandwidth bottleneck is unyielding.
It is. TurboQuant provides a rigorous mathematical framework to decouple sequence length from hardware latency, proving that you can achieve near-optimal compression without sacrificing online inference speed.
It definitively solves the immediate bottleneck. But there is an intriguing theoretical thread the authors mentioned just in passing that really warrants further exploration.
Oh, the entropy encoding part.
Yes, they note that they deliberately omitted entropy encoding, like applying Huffman or prefix codes to the code word indices.
Right, because the optimal continuous k-mean centroids reside at different distances from the mean, they inherently have different probabilities of being selected.
Exactly. Applying entropy encoding could mathematically compress the average bit width even further, completely losslessly.
But the authors opted against it to prioritize sheer processing speed. They noted that in their specific empirical tests, entropy encoding only reduced the average bit width by approximately 5%.
So the latency overhead of dynamic length decoding on current GPUs just outweighed the modest compression gain.
Right, for data centers it didn't make sense.
But consider the trajectory of edge device inference. As we attempt to deploy massive language models natively on local, highly constrained hardware environments, memory bandwidth tightens way beyond data center limits.
That's a great point.
Could a highly specialized, hardware-accelerated entropy encoding unit fused directly at the silicon level with TurboQuant's rotation matrix capture that remaining probabilistic slack?
I mean, could a hardware-software co-design push the limits of Shannon's bound even further, achieving a sub-1-bit effective regime for the KV cache without shattering the inner product fidelity?
It is a profoundly provocative vector for the next generation of accelerator architecture, taking mathematically flawless compression and searing it directly into the hardware, something to think about as you optimize your own pipelines.